Okay. So it's 7:30, guys. We'll go ahead and get started. So everyone, you're here for Organic Chemistry 1, right? Or maybe you're here for Orgo 2 to review for your ACS. But we're in Orgo 1 right now. So what I'm going to do is I have a practice exam made out right now. And you could find this practice exam on ucfsarcstudyunion.wordpress.com. Just in case you want to follow along on your laptop. What the plan is for today is I'm going to go through chapters 1 through 5 in about 15 minutes, and I'm going to devote the rest of the time to synthesis and spectroscopy, and then I'll open up to like Q&A. Oh, and I have radical reactions as well. And then I'll open up to like a Q&A. You guys could kind of ask anything. And the thing that's going to be a little different from our typical SARC sessions is that, unfortunately, it has to be kind of lecture style, just because we have to cover so much material, but I'm going to try and make it as interactive as possible. So we start off with a meme. Hopefully you're not writing Hakuna Matata on your exam. But I'm going to come out a little bit. Okay. Oh, and also I'm taking Organic Chemistry 2 right now with Dr. Frazier, and he communicated to me. I went to his office today and we were talking, and I'm going to emphasize arrow pushing with you guys and intermediates, and I'm going to introduce some like kinetic concepts to you just because me communicating with some chemistry professors, they're wanting me to introduce this to you guys just because they see a lot of issues in Orgo 2 with arrow pushing, intermediates, and kinetics. So I'll just kind of introduce it a little bit to you guys. So we'll start with question 1. Write the condensed formula for the following molecule. So what we do is on this line here, we have a carbon and 3 hydrogen. So that's CH3. We go to the next side. That's a carbon with 2 hydrogen. So we write CH2. We get to another carbon with 2 hydrogen. Hydrogen, hydrogen, that's CH2. Then we get to a carbon. This has 1 hydrogen, CH. When we have something branching off, how do we write that? Yeah, perfect. We put that in parentheses. So we have our alcohol in parentheses, and then we have our last CH3 down there. So if you're asked to put something in condensed formula, that would be how you do so. And when you have some written response exams, whether it's Orgo 1 or Orgo 2, you could be given condensed formula and asked to do a reaction, a synthesis problem with that. So you have to know how to quickly convert between condensed and line bond. I'll go to the next one. Complete the following acid-base reaction. Indicate which side equilibrium favors and why. So before we get into this type of reaction, what is this called, this functional group? Ketone. Yeah, perfect. That's a ketone. And you can't really see my meme, but that's Michael Keaton and then Michael Ketone with a ketone on his face. But with ketones, what we're going to do, water can serve as an acid or a base. So in this case, water is going to serve as an acid, and we're going to protonate this oxygen because this oxygen is partial negative, whereas this carbon, our carbon center, is partial positive. If we go over here, this oxygen is partial negative, and our hydrogen is partial positive. So negative is going to pick off something that's positive. That's really... Organic chemistry could be overwhelming, but a lot of it is just negative things picking off positive things. And that's honestly how I think of it to myself when I'm taking exams. So this oxygen is going to be more attracted to picking off a hydrogen than this carbonyl carbon. So what we're going to do is we're going to draw a line from high electron density to low. So from our oxygen to our hydrogen. And then we have another arrow breaking this bond between the hydrogen and the oxygen. And that's going to give us a product that looks like that plus OH. And this is going to have what kind of formal charge? Yeah, perfect, negative. Oxygen is neutral with 2 bonds. negative charge with 1 bond, positive 1 charge with how many bonds? Oxygen has a positive 1 charge with how many bonds? 3, yeah, perfect. So we completed our reaction here. And now we're asked to decide which side equilibrium favors and why. So what we're going to do is we're going to compare our base to our conjugate base and our acid and conjugate acid. So we said that our water functioned as our acid, our ketone was our base, our molecule here was our conjugate acid, and our hydroxide was our conjugate base. So now what we're going to do is we're going to compare our base to our conjugate base. And we're going to use that, we're going to do that using something called ARIO. I'm not sure if you could see this here. ARIO. So if you guys remember, this stands for atomic weight, resonance. What's I? Yeah, perfect, induction. And O is orbitals. So if we compare our ketone to our hydroxide, we see that our ketone has resonance capabilities. So this double bond here, we can bring it up to the oxygen. We can do many things with it. Whereas we can even bring it down and make an enol, which you guys do in like chapter 15 or earlier. Whereas where our hydroxide, we don't have any resonance capabilities. So equilibrium favors our reactants, because our base is more stable due to resonance. Equilibrium favors reactants due to resonance, stabilization. So if you're on an exam, more than likely they're going to ask you to answer this question in regard to ARIO, like with multiple choice. Another way that you could have done it, though, is if you compare your acid and your conjugate acid, your acid is unstable because it has a positive charge on this oxygen, whereas water is pretty stable. There were no charges on it, so it's going to favor the more stable side. So that was another way you could have been able to tell that favors the reactants. But like I said, if you're on a multiple choice, they may ask you in regard to ARIO more than likely. Can I turn the page? Does anyone have any questions on that? You're good? I know, it's like throwback. Okay. Which of the following has highest boiling point and why? So in order for us to answer this question, we have to know some things about boiling point. So what makes something, what causes something to have a high boiling point? And that's going to be our intramolecular forces. Our intramolecular forces are dispersion force, dipole-dipole, ion dipole, and hydrogen bonding. Other things that contribute to a high boiling point is more carbon atoms gives higher boiling point, but more branching leads to lower boiling point. So out of our options here, we see that this one has this big branch. Compared to the others, that's an unlikely answer because of that branch. So we know this isn't one of them. If we look at our other options, we see this has a lot of carbon, this has a sulfur. This one, it has hydrogen bonding capabilities because of this oxygen and hydrogen. So this is going to be our highest boiling point due to hydrogen bonding capabilities. And just as a reminder, H bonding occurs between hydrogen to fluorine, oxygen, or nitrogen. So because this hydrogen can form those bonds. And the way that I kind of remembered this is H bonds just want to have fun. So like you don't need to like Dolly Parton, but that just helped me remember. Does anyone have any questions? I know there's kind of like a Chem 2 throwback way intramolecular bonds or forces, sorry. Everyone's good? Okay. So now, hey Nicole. Now we're going to move to Newman projections. Draw the Newman projection from the following molecule. So when we're doing this type of problem, it takes a little bit of visualization. So we're looking at the molecule from this angle. So first I'm going to start out by drawing just a big circle. I'm going to put a dot in the middle. And we're going to start out with what's in front. And whatever's in front, we're going to have hooked onto this middle dot. So our hydrogen is in the plane. Our chlorine and methyl are kind of going in or out of the plane. So our hydrogen's in the plane, so it's going straight up. Our chlorine, we're looking from this direction. It's on a wedge, so that means it's coming out of the page, so it's going to our right. So it's going up and to the right. Can everyone see that, like kind of visualize that? If you're looking at our methyl down here, it's pointing down, of course, but dashes are going into the page. So if I'm looking at something from this direction, a methyl is going into the page, so it's going to the left. So the methyl is going down and to the left. Now we go to our back. These back compounds, we're going to draw on the circle part instead of the dot. That's the most educated way I can say it. So if we're looking at our bromine, it's going up, right? And it's on a dash. So that means it's going into or out of the page? Into, yeah, perfect. So it's our bromine is on a dash, so it's going into the page. So if we're looking from this direction, it's going into the page, it's going to the left, right? So up and to the left. Oops, well, that should have been from here, but up and to the left. Pretend that's not there. Okay. Now our hydrogen is in the plane. So we go down and we draw our hydrogen. Because it's in the plane, it's not going left or right. Our alcohol here, it's on a wedge, so it's going in or out of the page? Out, right. So if I'm looking this way and something's coming out of the page, it's to my right. So it's going down and to the right. Does anyone have any questions on Newman projection? You can all kind of form that. Yes? Went through it one more time? Yeah. So whatever's in the plane, we're going to have pointing straight up or straight down. So our hydrogen was in the plane, and it just was going up, so we just put it up. This other one was in the plane, so we just put it pointing straight down. Even though it looks like it's on an angle, they could do that to try to just trick you. Because it's in the plane, it's just going straight down. Whatever's on dashes is going into the plane. So since we're looking this way, it's going into the plane, so it's to our left. Wedges are coming out of the page, so if you're looking from this direction and it's coming out of the page, it's to your right. Wedges, yeah. Oh, I'm sorry if I said that. Yeah. Did that make more sense? Yeah? Okay. If we move on to 5, determine the conformational states of the following Newman projections and rank them from most to least stable. So we could just start with this one. What do we call this kind of conformation? Yeah, so that one's eclipse. No, you're good. I think there are different types of eclipse, right? Like staggered eclipse or something. I don't remember the names. I just know it by eclipse. Okay. So yeah, this one's eclipse, and this is very unstable, right? Because these atoms are very close to each other. They would really kind of repel each other, and they're not happy being that close. So eclipse is the, yeah, perfect, least stable conformation. This one, what is this called in the middle? Yeah, so this one, it's staggered or like anti, and this is the most stable. Your professor may call it like different things. So always anti is your most stable conformation. How about the rightmost? What is that called? Gauche, yeah, perfect. So this is gauche conformation. And this is kind of like middle stability. So if I was to label this 1, 2, and 3, our stability would be 2. It would be like that. So anti is most stable, followed by gauche, followed by eclipse.
What's the difference between anti and gauche?
Anti and gauche. So over here we see that we have a methyl pointing down and an ethyl pointing up. And they're anti to each other. And these are our most electronegative atoms in the molecule. So that makes it very stable that they're pointing away. Whereas with gauche, they're kind of far from each other, but they're not as far as anti. So that would give it middle stability, because it's, for them to be this far apart is more stable than for them to be like this close by with the hydrogen.
For sure.
Is that okay? Okay, perfect. Does anyone have questions on Newman projections before we move on? We're good? Okay. Now we're making good time. Okay. So draw the chair conformation of the following structure, trans 2-ethyl 1-methylcyclohexane. So chair can only be done with cyclohexanes. If we were to first draw the cyclic structure, it would be, we have an ethyl on 2 and a methyl on 1. You could choose whatever you want as your methyl or ethyl because this doesn't have double bonds. It'll just be symmetrical. So I'm just going to put a methyl on carbon 1 and an ethyl on whatever for carbon 2. So this is 1, 2, 3, 4, 5, 6. I made my carbon 1 into a wedge and my carbon 2 into a dash. You could have done carbon 1 as a dash and carbon 2 as a wedge. It doesn't matter, just as long as they're trans, right? So trans just means you have 1 on dash, 1 on wedge. When you do chair conformation, how do you make something trans? It has to do with axial and equatorial. So it has to be either axial and axial, or equatorial and equatorial. If you're doing something cis, I'll write cis down here, you're going to have axial and equatorial. So now we'll draw this. Now chairs can be kind of challenging to draw, but what I usually do is I go up at an angle, then I go up at an angle. This one is it doesn't come up as much this side, so I go up here. This is shorter than this one, so I go down here, and then I just connect them. You may have a different way that you do it, but you know, I don't have the nicest chairs, but you know, that's usually how I do it. Now you could again make anywhere carbon 1 or carbon 2. I'm just going to make this carbon 1, and I'm going to do it I'm just going to make it axial. So you could choose axial or equatorial. So I'm going to do axial on carbon 1, and then carbon 2, I'm going to make it axial, so pointing down. That's our methyl, and that's our ethyl. If I had done it equatorial, it would have looked something like this. So axial is pointing straight up, whereas equatorial is on an angle. If we had done it cis, Then I'll kind of do it to the side over here. This side goes down, up, and then connect. That's an ugly chair, but I could have chose for carbon 1 to be here, and it would have just been our methyl on equatorial and our ethyl in axial. So it doesn't matter what you make carbon 1, carbon 2, you just have to make sure you have one axial, and one equatorial. Does that make sense? Yes?
Why is it for chair confirmations, cis is axial and equatorial when normally like cis would be like both?
The same, right?
Both.
Yeah, so that's something that's kind of strange about chair confirmation. You'll have axial and axial or equatorial for trans. It could be the axials repel each other. Like, I'm not sure of the exact reason why. Like, I would want to look it up. I know the rule to it, but yeah, I would like to look up why also. Did anyone have questions on that? Is everyone good before we jump into substitution? Yeah. So, oh, and that's my little, if you see Facebook Messenger now, it's really a chair confirmation. So, it's probably not really, they probably just did a symbol, but. So I have a little note here to show a handwritten table. We could go over what makes something SN1 or SN2. So before we jump into actual reactions, we have two types of substitution reactions, SN1 or SN2. We're going to just briefly compare and contrast them. So if you remember, SN1 is stepwise, whereas SN2 is concerted, which means it happens in one step. Okay? And you could see this maybe on an exam, so just know that term concerted, that just means it happens in one step. You may also have something like SN1 is unimolecular, whereas SN2 is bimolecular. SN1 only occurs on secondary or tertiary structures, whereas SN2 only occurs on primary or secondary. SN1, you can have methyl or hydride shifts, whereas SN2, you don't have time for methyl or hydride shifts. It just all happens in one step. SN1, it could be paired with a polar protic solvent. I have another table for that too, so it's kind of getting in like table within table within table, but they should be kind of helpful. But yeah, they're with polar protic solvents, whereas SN2 is with polar aprotic. And I'll show you that table, so we'll get back to that. SN1 is paired with a weak nucleophile as a reagent, whereas SN2 is paired with a strong nucleophile. I would just warn about this step. This is kind of a general rule when you see it. It's just if these reagents are alone that you're going to know SN1 or SN2. But if they're paired with a certain type of solvent, you're going to go with whatever, like if you have a strong nucleophile with a protic solvent, it's going to be SN1. So don't just go by a strong nucleophile. If you have a strong nucleophile with something that is a tertiary structure, SN1 can't occur. So strong nucleophile with a tertiary structure, it has to be SN1. So just use this over here just as a general rule. The last thing that we would want to remember is that SN1 forms a racemic mixture, meaning dash and wedge plus enantiomer, whereas SN2 just has an inversion of configuration, so it does that backside attack. So I have an example down here because HBr, like hydrogen with a halogen is something that I see a lot of students kind of get tripped up on whether this is a strong or weak nucleophile and how to react it here. So if you have a structure like this was just originally this. And you have it with HBr, it has to be SN1 because OH is what kind of leaving group, good or bad? Yes, very bad leaving group. So you have to protonate it first. So I protonated my oxygen with the hydrogen, and that formed water, which now the oxygen has a formal charge of +1 because it has 3 bonds. Then water, is it a good or bad leaving group? Yeah, it's a good leaving group. So we had water leave, and it turned into this secondary carbocation. Now, remember, when we have an SN1 reaction, we can have methyl and hydride shifts. So we have a methyl right here and a hydrogen. I could draw it here, maybe a little clearer. We have a hydrogen hanging out over here too. So we did a hydride shift to stabilize that carbocation to then give a tertiary instead of a secondary carbocation. So why did we do a hydride shift instead of a methyl shift? Had we moved the methyl from here to here, it would have given another secondary carbocation. So when you're doing these methyl and hydride shifts, just make sure you're really stabilizing it instead of just like moving stuff around. So then we just attack with our bromine and we get there. Okay? Does anyone have questions on this reaction? Because just through the semester I saw some questions about hydrogen with a halogen. Does anyone have questions on that? No? Okay, perfect. So I just want to briefly show you my table on polar protic and aprotic solvents. Some of these may not be covered in your class. Oops, that's the wrong table. Some of these may not be covered in your class. Where is my table? Oh, so it seems as though I do not have my table on me. But if you go to, the SARC WordPress site, I have a whole list of the polar protic and aprotic solvents that are just kind of laid out there. I'll give you just a few examples. So an example of a polar aprotic solvent would be like DMSO, DMS, and you have a few more. Some examples of polar protic solvents would be like ETOH, so ethanol. You could have water there. You could have different ones. Kind of a way that I remembered this, if you have protic, that means you have a hydrogen. Aprotic means you don't have a hydrogen, right? Because proton is H+, it's hydrogen. So a lot of your polar protic solvents are going to look kind of like regular reagents, whereas your polar aprotic solvents are going to just look weird, like DMSO and DMS. So they're just going to be like weird sounding things. Okay. So now with this, I'm going to go ahead and get into our substitution reactions. Complete the following reactions and indicate if they proceed by SN1 or SN2. So this right here, is this SN1 or SN2? SN2, perfect. SN2. Bromine is a way better leaving group. Methyl doesn't leave, so bromine is going to leave, and our chlorine is going to come in, do a backside attack. And remember your inversion of configuration. So this is now going to become a wedge. We don't touch this. So this was a wedge, and it stays a wedge. We only do an inversion of configuration on the atom that we're attacking. Now what about B? Is this SN1 or SN2? Okay. Is this SN1 or SN2? SN1, perfect. So we have NAI. This is a strong nucleophile. Oops, I spelled strong wrong for whatever reason. But this is a polar protic solvent. So we have a strong nucleophile, but it's paired with a polar protic solvent, and that's going to make this an SN1 reaction. What else makes it SN1? This is a tertiary structure. So SN2 doesn't occur on tertiary structures, it's only on secondary or primary. So bromine leaves. We draw out our molecule once again. This lost its dashness, I'll just call it. So it went from a dash to now being in the plane, because you can't have a dash without a wedge or a wedge without a dash. And there's a carbocation right there. And now we go with our I, and it attacks. And we have I. Some professors let you put plus enantiomer. So if you see plus enantiomer, that's fine, or you may have to like write it out, and that'll look, just your I is now on a dash and your ethyl is on a wedge. Does anyone have questions on that? Can you see that, by the way? Should I make it closer? That says EN, by the way, for enantiomer. I don't know what that looks like. An N with like a bag. So, is everyone good to move on to elimination? Yeah? Wait, oh, okay. And I'll have, you guys can feel free to come up and take pictures of these at the end as well. So, I'll have the whole answer key for you guys. Can I? Okay, perfect. Now we're going to get into elimination. Predict the products and note whether the following proceed by E1 or E2. And note Zaitsev and Hoffman products. So Zaitsev means it's the more substituted product. Hoffman means it's the less substituted. So just because you have a Zaitsev product doesn't necessarily mean it's your major product. And just because you have a Hoffman product doesn't mean it's your minor product. We're going to see an exception. So typically your Zaitsev is your major and your Hoffman is your minor, but we're going to see an exception to this rule. But for now, we have A. So what happens here is our chlorine is a good leaving group. It goes ahead, we have a hydrogen hanging out right over here. Our O from our OMe is going to pick it off, and our hydrogen is going to form a double bond right there. So, I mean, I guess I should have drawn the order of picking off the hydrogen, hydrogen forming the double bond, and then the double bond formation is going to cause the chlorine to kick off. So that's going to be something that looks like this. How did I know that it was all going to occur in one step? It's an E2 reaction because this is tertiary and it's a strong base here. So we have that. We also could have formed something like, I'll kind of draw it down here. Can you guys, oop, too far. I also could have done something like this, NaOMe. This methyl here has 3 hydrogen on it, right? We know that. So I'll just draw hydrogen, hydrogen, hydrogen. This O could have picked off a hydrogen, and a double bond could have formed right there, and the chlorine pops off. And we would have gotten something like that, a double bond right there. So these are our 2 products. Maybe I should make our double bond longer. Those are our 2 products. What's our Zaitsev and what's our Hoffman? Yeah, perfect. So this is our Zaitsev, which in this case is our major product. And this is our, that of course leaves this as our Hoffman product, which is our minor product. And like I said, I talked to Dr. Andrew Fraser before this class, and he told me to note to you thermo and kinetic products. In this case, this is much more stable, our Zaitsev, than Hoffman in this case because it's more, this double bond is in the more substituted area. So this is a note for Orgo 2, but just so you're familiar with it, this is our thermo product. Whereas this is our kinetic product because the double bond forms in the less substituted area. It forms more quickly, but it's not as stable as our thermal product. This takes more energy to form, but it's more stable. Does anyone have questions on that? You're good? Now we go with tert-butoxide. Tert-butoxide. So tert-butoxide, when it's acting on a tertiary structure, what does it do? E1 or E2? Yeah, perfect. This is an E2 reaction. So we're going to have, oops. So what happens here is kind of the same thing. We have our hydrogen hanging out over here. Our O, what the O here kind of looks like is just this. That's like tert-butoxide without the, we have potassium, a positive potassium hanging out, but this is going to go and pick off our hydrogen that forms a double bond, and chlorine kicks off, and we get something that looks like this. Or we could have gotten we have hydrogen here, hydrogen here, hydrogen here. This goes and picks off a hydrogen, and it forms a double bond right there. These are methyls, not a double bond. So what is your Hoffman and what is your Zaitsev product? Yeah, perfect. So this is your Hoffman. This is your Zaitsev. What's your major product? Hoffman, because it's tert-butoxide. Tert-butoxide, your less substituted is your major product. That's the exception to the rule. And just pointing it out again, the double bond is on the more substituted area, so this is your thermo product, your thermodynamic product, and this is your kinetic product because your double bond is in the less substituted area. There you go. Did everyone feel good about that? Sorry if my handwriting's bad, I can interpret the scripts. So. By the way, this is a helpful table that I got. It's not from your book, it's from the Klein book, but I like it. So I'm not sure how well you can see that, but you could come up and take a picture later, and it just helps us keep track of weak base, weak nucleophile, what you do, SN1 or SN2, E1, E2. You could come up and take a picture of this after. It's very blurry under the .cam, but yeah. Something that, as I've been saying throughout the semester, that Dr. Hashim, your professor, yes, Dr. Hashim, tert-butoxide, something that she wanted me to note with tert-butoxide is that if it's reacting on a primary or secondary structure, it does E1, or I'm sorry, it does E2 or SN2. If it's a tertiary structure, it's only E2. If you're doing synthesis, it'll only be elimination. So if you're doing synthesis with tert-butoxide, it's only elimination. That's something that Dr. Hashim wanted me to note to you guys. So I'm going to turn. So now we have Kohn-Ingold prelog system. Don't be like overwhelmed by that name. It's just naming. So that just means we're using RNS systems. I'm gonna make it big. So we assign RNS configuration only to chiral centers. So where are chiral centers in this molecule? Yeah, so this is our chiral center. So this, Yeah, so this has a chiral center because for it to be chiral, it has to have 4 different groups attached to a carbon. So this has an ethyl, this has a bunch of stuff, it has a hydrogen, and it has a bromine, so this is chiral. If we look at this carbon over here, this group is different from this group. However, we have 2 methyls, so it's not 4 different groups attached to one carbon. Likewise, over here, we have a bunch of stuff over here. We have a methyl, and we have a hydrogen. So because we have 2 methyls hooked onto this one carbon, it's not going to be chiral. So we don't name R and S. Even though we have dash and wedge, we don't name R and S. So the only chiral center is this one right here, and we're going to assign configuration to that one. So since bromine takes priority in this case because it's very electronegative, it's very heavy, we're going to put a 1. That's going to be our priority. Not necessarily because it's on a wedge, it's because bromine is the highest priority over an ethyl and over this stuff. So for us to assign priority to number 2, we have to go 1 carbon out at a time and compare them. So this, if we come out over here, we have a carbon, a hydrogen, and a hydrogen. If we compare to over here, we have a carbon, a hydrogen, and a hydrogen. If we go out again, we have a carbon. It doesn't have any hydrogen connected to it, right? Because carbon can only have 4 bonds. It goes to a carbon, and it has hydrogens. If we go over here, this is a carbon with 3 hydrogen. So these are equal. When we go to this next one, these carbons are tied, but carbon beats hydrogen. So that means this is our second priority, whereas this is our third priority. We have a hydrogen here also that we don't draw, but the hydrogen doesn't really matter because we know it's going to be our lowest priority. So like we don't even care about hydrogen. It's sad, but we don't care about it. So it's going in this direction, which is, that's clockwise, right? Yeah. So that's clockwise. That's R or S? That's R, perfect. So our bromine is R. Yeah, that's a good R, right? So, yeah, that's a quality R. So now we have to assign carbon 1, 2, 3, and all that. So if we compare this side, this is the first one to branch. So this is carbon 1, 2, 3, 4, 5, 6, 7. I'm going to kind of cross those out because I don't want to get confused. We chose, this has a bromine here, but we chose this as carbon 1 because it's the first one to have a methyl branch, or a branch in general. Whereas this, if we go to what may have been carbon 2, it has no branches, so it's just nothing to us. It's carbon 6, not 2. So 1, 2, 3, 4, 5. We have on carbon 5 is our chiral center. So at the very beginning of the molecule, we write 5R in parentheses. Then we do a dash. What I like to do after this, since we have to do it in alphabetical order and like, I don't know, the alphabet's not my thing, I just count. So on carbon 2, we have a methyl. On carbon 3, we have 2 methyls. So I'll write like 3,3-dimethyl. Carbon 4, we have nothing. 5, we have a bromine, which we'll call bromo. So what we're going to do is now we're going to put it in order. B comes before M. We don't worry about the, what is this, a suffix? I'm not an English major. Prefix? Okay. Oh yeah, suffix is at the end, right? Okay, yeah, that thing. So we don't take the prefix into account when we're naming. So we look at the methyl and we compare it to bromo. B comes before M. So 5 bromo. Then we have 2, 3, 3 trimethyl. And this had 1, 2, 3, 4, 5, 6, 7 trimethyl heptane. We didn't have any double bonds. It's an alkane, so it's ane. If it had a double bond, it would be ene. 7 is hep. So we do have to keep those in mind. Okay. Is everyone feeling okay? Okay. So now is the part of the class that people tend to get overwhelmed with. And that's going to be synthesis reactions. So to give you kind of a rest, I have just pet sweet fruit underhead to kind of calm you for a moment, and we're going to do some synthesis. To not be as overwhelmed with this, I gave you some tips. So when we're doing synthesis, just remember negative things go to positive things. We draw our arrows from high electron density to low. On my last organic 2 exam, I just kind of guessed on a question, but I got it right because I knew that negative things go to positive things. So as long as you know that, you're going to be okay. I'm not a bad student. I just had another exam. Um, also remember, OH is a bad leaving group. Don't be ashamed to count in your carbon. Professionals do it also. Everyone does it. So yeah, don't be that guy that didn't count the carbon. Watch for hydride methyl shifts and study a little bit each day. If you try to like study 2 hours before the exam, yeah, you might if you're like, but yeah, no, don't do that. Okay. So now I have a little note, show anti-syn addition, Markovnikov, anti-Markovnikov table. So you can find this on the WordPress site. That's as far back as it goes. I'm just going to briefly show this to you. So if you go to ucfsarc.wordpress.com, this is where you'll find my polar protic and polar aprotic solvent list too. I have this review of syn anti-addition and Markovnikov, anti-Markovnikov. We don't have enough time to cover all of these, so just go to that site and you can see, you know, the ones that you have to know. If this is more or less than you have to know, then, you know, you just have to refer to your professor. But yeah, I have 2 pages of it. So syn addition, anti-addition, depends if it's hydroxylation, and certain rules around syn and anti-addition. And also like certain things that are always anti-Markovnikov, such as hydrogen peroxide, and certain things that are always Markovnikov, like acid, dilute sulfuric acid, and stuff like that. So yeah. Just as a note, there's the site again if you want to go to it. So now we'll go further, and we'll get into some synthesis. So let's get a little closer. So we're going to compare and contrast concentrated and dilute sulfuric acid in the following reaction. This is question 10, right? Yeah. So dilute sulfuric acid, does that do substitution or elimination? It does substitution. So it's a Markovnikov reaction. So what's going to happen? Oh, you could leave it like this, but the way I like to do reactions with dilute sulfuric acid is by just making it acid. So an acid, another way to write that is H3O+. So what I'm going to do is this double bond, the electrons are going to take a hydrogen, because high electron density to low electron density, point your arrow that way. And then your bond is going to break between the hydrogen and oxygen. Since this is Markovnikov, we're going to get a carbocation in the middle, so it's tertiary. And then if we react this with water, we lost the hydrogen, so now we only have 2 hydrogen left. So we have water. This is going to go in attack. Now we have water with a positive charge, and we can come back with our water to then deprotonate and form that product. Is that messy? So what you can remember with dilute sulfuric acid is that you're going to put an OH on the most substituted area because it's Markovnikov. I just showed you the mechanism for it. So we make a carbocation intermediate on the most substituted area. We added water to the most substituted area, and that causes the oxygen to have a positive charge, a positive formal charge, because an oxygen with 3 bonds has a formal charge of +1. Then I just deprotonated. I took out a hydrogen from this using water, and we got that. You may be wondering, how can you just keep coming back with water? When you have water, you can, because water's special like that. You could just keep coming back and back and back with water. Okay? Does anyone have questions on that? You're good? Okay. If I'm going too fast, let me know, by the way. So now we have concentrated sulfuric acid. What's the difference between dilute and concentrated sulfuric acid? This is going to do elimination. So concentrated sulfuric acid does elimination. I'm going to turn the page here. So what this is going to do is we're going to get a carbocation intermediate. Oh, I'm sorry. We're going to pick off a hydrogen because we're doing elimination. So something good to note here, and I have OH as a good leaving group here too. This is going to do elimination because it's going to make OH a good leaving group. So I'm just going to draw, I like doing sulfuric acid, just writing it as acid because otherwise you have to put the S and everything. So this oxygen is going to go and pick off a proton because acid has that positive charge and it's unstable. And this oxygen has a partial negative charge, so it's going to be attracted to that hydrogen. So what's going to happen then is you're going to have something like this. It forms water. Now water is a good leaving group. We went from alcohol to water, so now it's a good leaving group. Water can leave. And while water leaves, we're going to do an elimination reaction formed at the most substituted area. So while water leaves, we're going to come back with water from a concentrated sulfuric acid, and we're going to pick off a proton and form a double bond right there. And that's going to give us something that looks like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2. It's going to give us right there. Yeah, it's going to give us something that looks weird like that. 1, 2. Yeah, I put that in the right area. Can everyone see that clearly? So you could just get rid of the OH, but I'm just showing you how it happens. We protonated our alcohol to make it water. Water left, and we made water leave by picking off this proton and forming a double bond there. And we did it at the more substituted area because that's the most stable area. Is that good? Yep. Now I have some more reagents that make OH a good leaving group. So we know concentrated sulfuric acid is one of them. POCl3 is another one. So what this is going to do, we don't learn the exact mechanism for it, but POCl3 with pyridine, it's just going to form it's just going to get rid of water, make it a good leaving group, and form a double bond. And it didn't matter where we put the double bond because the whole thing is just symmetrical. This is something you want to remember for Orgo 2. This comes back, POCl3. This one too. If we go on to B, what does this do to alcohol? Yeah, it makes it a good leaving group, and we substitute it with bromine. So if we notice this one up here, I'm spelling it wrong. This is elimination with sulfuric acid. This one was elimination. This is substitution. And now this one, we're going to do substitution again. We don't know the mechanism. We don't learn the mechanism for this one. You literally just like switch this for a bromine. Now with this one, what do we replace the OH with? Yeah, so OTS. So we switch it with OTS. Yeah, it's perfect. So this is like the best leaving group you can have. So OTS leaves, and then you have NaOMe. This then does a substitution reaction. It goes and it attacks, and you're going to get 1, 2, 3, 4, 5, choo-choo. And this is going to form oxygen with a methyl on it. So you could write it with a methyl, or you could write it with an OMe. It's the same thing. So you can see it both ways. Is everyone good with that? This is a very popular reagent. So remember that. Does anyone have questions on that? You're good? Let's see how much time we have. Okay. Perform the following reactions and indicate if they proceed by Markovnikov, anti-Markovnikov, syn addition, and or anti-addition. So this reagent over here, this BH3THF, this is syn addition. And this H2O2 is anti-Markovnikov. I'll just write anti-Markov because I'm lazy. And so what we're going to do is, because it's anti-Markovnikov, we're going to do substitution to the less substituted area. So BH3THF is going to create a carbocation intermediate. So step 1 is going to be creating a carbocation right here, because that would be less substituted than putting it here. So those are our two options. Here or here. We put it here because it's less substituted. Then we go with step 2, which is H2O2 at NaOH. So NaOH, our OH is going to go and attack, and that gives us that. If we move on, we have an alkene with MCPBA. What happens when you have an alkene with MCPBA? What do you form? Yeah, perfect. You form an epoxide. That's going to come back, again, very, very strong in Orgo 2. You want to know that forever. So we have our acid here. And typically, when you're opening an epoxide, you're going to attack at the less substituted area. In this case, it doesn't matter because they're both equally substituted. So I'm just going to break it off. And we're going to get something that looks like this. It's an oxygen with a negative charge. And in this side, it's water. So now you can do this in one of two ways. You can either come back with water and protonate your negatively charged oxygen, come back with water again, and deprotonate your this one or this one. Or what you can do as a little shortcut is you could do a proton transfer. So this is negatively charged, this is positively charged. Just pick off a proton from right there, and you get OH with OH. So you could do it, if you want to do it the long way, you can. Like, don't do this if you don't feel comfortable. But this is just like a big shortcut. Transfer. I spelled transfer wrong. Transfer. Proton transfer. Does that make sense to everyone how that happened? Yeah? Is that a big shortcut from what you've been doing? Or you've been doing it like that? It makes sense, right? Yeah. Oh, also, we should be noting if it's syn or anti-addition. So I'm sorry, if we go back to this one, this is syn addition. So we would have done like both on dash or both on wedge. So like I'll just make them both on wedge. Yeah. And then we won't have plus enantiomer because if we flip it and, not plus enantiomer, because if we flip it, it's just going to be a meso compound. So no enantiomer due to meso compound. So you just have like, there'll either be both wedges or both dashes, but you won't have this plus its enantiomer. If we do MCPBA, that's anti-addition. Anti-addition, and this is Markovnikov. Our acids are Markovnikov. So in this case, you would have one on a dash and one on a wedge, and we would do one on, I kind of did a backwards wedge there, but you get what I'm you get what I'm saying. There we go. So that's anti. Maybe I'll zoom out a little bit in case you guys are still writing. KMNO4, this is syn addition. So KMNO4, we don't really learn the mechanism for it, but what we're going to do is we're going to add an OH to both sides of the double bond, so with cold KMNO4. So OH, I'll make this a wedge and a wedge. And like I said, you could have done dashes. You're not right, or I mean, you are right, but if you do it the other way, you're not wrong. So yeah. And you don't have plus an enantiomer again because it will be a meso compound, because if you flip it, it's the same thing. So does anyone have questions on those, the syn and anti addition? You're good? Okay. How much time do we have? Okay, we have half an hour still. So what's more stable, cis or trans? Trans, perfect. So trans is always more stable. We're going to have one reagent that makes our product cis, and that's going to be Lindlar's catalyst. This is going to produce a cis structure. So remember Lindlar's catalyst. What this does is it picks off, well, this takes a hydrogen and you end up getting a cis structure. So you just get rid of one of the double bonds and you make a cis conformation. And I have a compare and contrast with H2 with Lindlar's catalyst versus H2 with a metal. So when you pair H2 with a metal, you're going to do this like a whole lot in Orgo 2 as well. You're just going to fully reduce your starting molecule. So you're not going to have any double bonds. This is going to be an alkane. So 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. And we have a methyl branching off. That's all you're going to do. You're going to draw the exact same thing with the exact same amount of carbon, but you're going to get rid of all of your triple and double bonds. Yeah? Anyone have questions on that? Should we move on? Draw the mechanism for the following tautomerization reaction. That's a scary word, but all it means is constitutional isomer. Specifically, you're going to be going back and forth between enols and ketos. So this right here, this is an enol, right? All an enol means is ene, you have a double bond, and ol, you have an alcohol. So what's going to happen is we have H3O+. We're going to make this into a keto. So we're going to go from an enol to a keto. H3O+. So this double bond is going to pick off a hydrogen. And we're going to get a carbocation intermediate at the most substituted area, which is right there. And what's going to happen now is an oxygen with a positive charge is way more stable than a carbon with a positive charge. So this, it has resonance capability. It's going to go and it's going to stabilize that carbocation. And it's going to form a double bond right there. But now because this oxygen has 3 bonds, it's going to have that positive 1 charge. We got rid of a hydrogen over here from our acid. So now we're going to come back with water. And we're just going to pick off that hydrogen. And we form, there, a ketone. So we went from an enol to a ketone. That's all you're doing. And this is a constitutional isomer, We have the exact same chemical formula. It's just we got rid of this hydrogen and instead replaced it with a hydrogen over here. So the chemical formula is exactly the same. Is everyone okay with that? Anyone have questions before we move on? We're good? Okay. Perform the following multi-step synthesis reactions. So what's another way to write XS? Yeah, perfect. So 2 equivalents is another way to write XS. Like Dr. Hashim says, that doesn't mean extra small, it just means excess. Like you have 2, you're in excess of something. We have NaNH2. What's another reagent we can use aside from NaNH2 to do the exact same thing? Exactly, perfect. So you could use NaH and it'll do the exact same thing. So what this does, we have excess of it, so it's going to pick off hydrogens and form double bonds. So instead of writing NaNH2, I'm just going to take my NH2. This has a negative charge on it, this nitrogen. We have a hydrogen hanging out over here on this chlorine, on this carbon the chlorine's attached to. I'm going to pick off that hydrogen, form a double bond right here, and that's going to kick off this chlorine. Notice I didn't kick off this chlorine, so you can't kick off the same leaving group that is attached to this carbon. So if you're taking this one, you have to go on the adjacent leaving group. Is that confusing or that makes sense? That makes sense? Okay. So we do it once there. We kicked it off. So we still have this chlorine, but we formed a double bond. We come back with our NH2. Now we have 2 hydrogen over here. I'm just going to draw one just so it's less messy. We're going to pick off that hydrogen. It's going to form another bond, and it's going to cause this chlorine to leave. So now we're going to have 1, 2, 3, 4, 1, 2, 3, 4, something like that. 1, 2, 3, 4. We don't want to draw alkynes bent. So you want it to be in a straight line. So that's why I made it weird like this, and I did 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have the same number of carbon. So yeah, don't draw your alkynes bent. It makes professors mad. Step 2, that was only step 1. Now we're going in with step 2 with another NaNH2. And what we're going to do is we have a hydrogen hanging out over here. We're going to pick that off and form carbon anion. Carbon anion is a negatively charged carbon. So that's step 2. Step 3, we're coming in with ETI. ETI is just another way to write an ethyl attached to an iodine. 1, 2, iodine. So in this case, our reagent is actually our electrophile, and this thing is our nucleophile, which is kind of backwards from typical reactions that we do. But in this case, this is our nucleophile. So we're going to kick off this iodine, and this nucleophile is going to go and attack the electrophilic area. And we're going to get something that looks like there. So we're just going to add 2 carbon on it. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. I just added 1 carbon, 2 carbon. Is that okay? Yeah. Is anyone confused by how it's drawn? Or you're good? That's good? Okay. Now we have this 9-BBN. It's going to do the same thing. Well, not the same thing as this one, but it's going to have the triple bond. One of them is going to take a hydrogen from 9-BBN. It's a really big structure, so we just know that it picks off a hydrogen. and it's going to form a double bond there. And we're going to have that carbocation on the less substituted area. Now if we come in with step 2, we have H2O2, which is anti-Markovnikov, and NaOH. So where NaOH, I'm going to come in and attack that carbocation. And by the way, that was why I put this on the less substituted area, because H2O2 is anti-Markovnikov. So we have something, I'm kind of running out of room, but we have something like that. At this point, are we done? So water, yeah, so we're going to come back with so why are we coming back? This is what? Yeah, perfect. It's enol. We're going to make it into a keto structure. So enols are much less stable than ketones. So that's why we're going to change this. So we're going to come back with like 9 bbn, and we're going to do the same thing and form a carbocation. I'm kind of running out of room, but I'm going to draw this the best I can. This is going to be 1, 2, 3, 2. We're going to form our carbocation intermediate right there. And then, which would be the less substituted area, because that would have been like putting it here. We just got rid of the double bond. And now our double bond, our lone pairs from the oxygen are going to go and stabilize that carbocation. And we're going to get 1, 2, 3, 1, 2, 3. And that has a positive charge. And now we can just come in with like our NaOH or with water and deprotonate that to make it stable. So like we'll come in with a base and deprotonate that to make it into 1, 2, 3, 1, 2, 3, double bond, and there. What functional group is this? Yeah, perfect. That's an aldehyde. So this is much more stable than the enol that we had over here. So be careful if you're given a multiple choice exam and you have this product and this one. It's going to be this product because it's more stable. So just be careful. That could be tricky. Yes?
Right there, is that a double bond?
This?
Over there on the corner?
This?
Over.
This? Yeah, I'm sorry. Yeah, that's a double bond. I'll do it like darker. Yeah. Perfect. Mm-hmm. Let's see. Did you guys want to do an epoxide question, or you want me to go into like spectroscopy? Spec? Okay. So epoxides, just practice that. So now you're done with synthesis. And now we're going to get into some spectroscopy. So I'm going to zoom out a little bit. So here are some rules about spectroscopy that I made, a little table. So if we're comparing mass spec to IR to NMR, NMR is like a little blurry, but mass spec, we're identifying the molecular formula and weight of a compound. Spectroscopy, you're identifying functional groups. With NMR, you're identifying the carbon-hydrogen framework. You guys could read the rest, like, because we're running out of time. We have like 15 minutes. This is on the Study Union WordPress site, so like you can look at this table if you want. But yeah. We're finding MZ with mass spec. Our M+1 peak is in regard to carbon-13. Yeah, this is something important to note that I should go over. Chlorine, it presents 2 peaks, an M+ peak and an M+2 peak in a 3-to-1 ratio of 35 to 37. Remember that chlorine is in a 3-to-1 ratio. If we have time, we'll do an example of this. bromine has 2 peaks in a 1-to-1 ratio. Bromine 79 to 81. So if you see graphs in a 3-to-1 ratio, you have chlorine. If you have a 1-to-1 ratio, it's bromine. And now we could do some NMR. We have 15 minutes left, so we won't be able to cover all of mass spec, IR, and NMR. Is there one that you guys want me to focus more on than the other? NMR, yeah. Yeah, that's what I thought. Okay. So yeah, you guys know how to find like base peak and all that. In this situation, what atoms specifically are present in mass spec? This M plus peak is at 60. This M plus 2 peak is at 20. It's in a 3-to-1 ratio, so that's what? Chlorine, perfect. 1-to-1 ratio, what is it? Yeah, perfect. IR stuff, this is just a table that I think you guys have to memorize. Like, don't take my word for it, but I think you do. So yeah, you could take picture, well, this is on the WordPress side, or you could take pictures after if you want, IR stuffs. So this is also a helpful way to remember, like you have hydrogen bonds, triple bonds, double bonds, and single bonds. It's kind of a helpful way to remember that table because you know it's going to be in these ranges. 400 range is like single bonds, whereas hydrogen bonds are in the 4,000 range. Okay? So now we're going to get into NMR. We're on question 13, right? I'm sorry, not 13. That's an 8. So one thing to note, we're going to do signals for HNMR. When we have signals, for HNMR, we do something called spin-spin splitting. For CNMR, we don't have splitting. So a signal is going to be produced when you have hydrogens in a different environment. So we have hydrogens here, right? We have CH3. We have a hydrogen hanging out over here. We have 2 hydrogens hanging out over here. And we have hydrogens hanging out over here. So how many signals are present in the following compound? The answer is actually not 4. It will be 5 because these are one on a dash and one on a wedge. So that's something to be careful with. You're going to have 5 signals here because you have that dash and wedge. So they're in different environments. Does that make sense? We'll go over how they're in different environments. Okay. So, so over here, this carbon with the hydrogen on it are in a different environment than this CH3, right? Because this is 1-2 carbon away from what's connected to the chlorine, whereas this one is just 1 carbon away from what's connected to the chlorine. So this is 1 signal. This is 1. This hydrogen, you can see it's in a different environment from all the other hydrogen. So this is 2 signals. I mean, this is, 1, 2. I'm just counting the signals, not that this one gives 2 signals. Yeah, I'm sorry, the way I worded that was weird. So then these, when you have one on a dash and a wedge, because they're kind of hanging out outside there, like just floating, this is going to give you 3, 4. So you're going to count each of these. 1, 2, 3, 4. You count each as a separate signal when you have dash and wedge. Is that confusing? Does that make sense? You get it? Yeah, so when you have dash and wedge, what was it? Yeah. Yeah. And then over here, we said it's in a different environment, so this is our 5th signal. So answer equals 5 signals. We have 5 signals. Does that make sense to you guys? I know NMR is a little, but yeah. Okay. Now we move on to 19. This is kind of good because it puts everything together. And I think we have time. Yeah, we have like 10 minutes still. How many signals are present in the following compound? So we want to first count our signals. Then we want to label singlets, doublets, triplets, quadruplets, whatever we have that's present. Like we may not have quadruplets, but we just want to label whatever's present. And then we want to graph the compound on an NMR spectrum if the hydrogens on carbon 1 and carbon 2 have chemical shifts at that ppm. I won't read it. So first we're going to count the signals, right? So this carbon has a chlorine, and then another bond here, so it has room for a hydrogen down here. This carbon has a hydrogen here, has a hydrogen here. So yeah, that's all the hydrogen we have. Yeah, okay, that's all the hydrogen we have. Now, are these hydrogens on dashes and wedges? Are you sure? They're in the plane, right? Because they're terminal. These are terminal hydrogens. You don't put terminal structures on dashes and wedges. So be careful. You see, everyone sees how this is terminal? No? Okay, I could draw it. If we have something like this, CH3, we call the end, like if you're on the end, you're terminal, right? So that's why this is terminal, because we have a carbon here, and then we have this carbon's attached to hydrogen, chlorine. So because you have a terminal, these two terminal hydrogen, they're not on dash wedge because you have a hydrogen, chlorine attached to this carbon. So you can't have like dash wedge and then like this weird chlorine hanging out, like floating around. So this is going to give two signals because you have this hydrogen that's in a different environment from this one, and these hydrogens are in a different environment from these. These two hydrogens are in the same kind of environment because they're not dash and wedge, they're in the plane, right? So to answer the question, how many signals are present in the compound? 2 signals. Now we want to label our singlets, doublets, triplets, quadruplets, whatever we have if present. So if we start here, we look at wherever we have adjacent hydrogens. So if we look over here, this chlorine doesn't have any hydrogen, this doesn't have any hydrogen. We look at this carbon, it has 2 hydrogen attached to it. So we do something called the N+1 rule. Oops, not rule. So this is 2 hydrogen plus 1 equals 3. That means this is perfect, this is a triplet. Then if we count from these, what they have next to them, it has this carbon that's attached to this hydrogen. We use the N+1 rule. N+1 equals 1 plus 1 equals 2 equals what? Doublet, right? So we have a triplet and a doublet. We don't have anything else present because those are the only ones that we have here. What else were we asked to do? Okay, so we were given the chemical shifts. So where do I have room to do this? Okay, I'm going to do it here. I'm just going to get a paper. So I'm going to draw a line, and what side is downfield and what side is upfield? If we go this way, yeah, perfect, downfield. This way, that means this is upfield. What happens to our ppm? So ppm is our x-axis, right? That's parts per million. Parts per million. So we're going to go from like 9, 7. You don't have to use these exact numbers, but upfield, you're getting into smaller numbers. Downfield, you're getting into bigger numbers. So just be careful with that. So we have, how much time do we have? Yeah, we have 5 minutes, so we have time to graph this. Graph the compound on an NMR spectrum of the hydrogens on carbon 1. So carbon 1 is what? This one, right? Because it's attached to 2 chlorine. So this chlorine, this carbon has a triplet, and it's at 5.77 ppm. So 5.77, let's just say it's like around here. And it's a triplet. So we're going to go 1 peak, 2 peak, 3 peak. So the middle peak is going to be the biggest. I did that really small, didn't I? Let me see if I can zoom in, because I drew that like really, really small. I'm not flipping you guys off. It's just, it's NMR. Like, okay. What was that? That's just how triplets are. It's just being a triplet. Triplets being triplets. Carbon 2 has a ppm of 3.95, so like that's whatever around here, and that's a doublet. So our doublets are going to be around the same height, right? If I zoom out for a second, notice that, oh, when I was naming the carbons, you guys couldn't see it, could you? I don't know. Well, anyway. This is carbon 1, and we do it with a triplet. So this carbon is what had the triplet. So carbon 1 had a 5.7 ppm. So carbon 1 had a 5.7 ppm because we're looking over here at its adjacent hydrogen. So you're not doing the one that's a doublet. You're doing the adjacent hydrogen. Does that make sense? Is anyone confused by that? You're looking at what's adjacent to the carbon. So if you want to graph this on NMR, you go to the adjacent hydrogens. And that's a triplet. So at 5.77, we have our triplet. Then we want to do carbon 2, which was at 3.95 ppm. 3.95 ppm, you go to your adjacent. That was a doublet, so you draw a doublet. Is that okay? Does that make sense?
Yeah.
Do you feel better about NMR now? Kind of? I know, because we only have 2 hours, so we can't do like so much in 2 hours, but I hope that was helpful. CNMR, let's see. We have 3 minutes, but this is a CNMR question. Really? Oh, am I going too fast then? Oh, I'm sorry. We're going until 9:30. Oh, I'm sorry. We have a lot of time then. I miscalculated. Okay. Okay, did everyone understand this then? I could take my time. We got a lot of time. All right. All right.
Repeat it again.
Repeat it again. Okay. Yeah, I'm sorry about that. Okay. Let's do NMR again. And so, okay. So you guys see how we calculated the signals, right? First, we looked at how many hydrogen we have in a different environment. This hydrogen was in a different environment. These hydrogens were in a different environment, but these hydrogens were in the same environment to each other. So we have 2 signals, right? 2 signals. Then we were asked to calculate singlets, doublets, triplets, quadruplets. So if we're wanting to count the singlets, doublets, whatever, of this one, we go to the adjacent carbon and count the hydrogen on there, and we use the n+1 rule. So we have 2 hydrogen, we do 2 + 1 is 3, and that's a triplet. If we want to find the doublets, triplets, whatever of this carbon, then we go to this one, the adjacent carbon, and we have 1 hydrogen hanging out over here. So we do n+1, 1 hydrogen, 1 + 1 is 2, and that's a doublet.
How would you ever get a singlet?
Oh, that's a good question. So we would get a singlet. Yeah, that's actually the example I was going to give. Yeah, perfect. So if you have something like this, an alcohol, let me just put like a methyl there. And so this hydrogen, does it have any adjacent hydrogens? No, right? So we do the n+1 rule. 0 plus 1 is 1, and that's a singlet. Does that make sense? Yeah.
And that's only for OH?
You could have, this could have been NH. So it's, you have a singlet when your hydrogen doesn't have any adjacent hydrogens. So if we looked over here, our hydrogen attached to this carbon had this other carbon that was attached to hydrogen, so it had its friends there. This one, it has no friends, it's a singlet. So it doesn't have anything that's adjacent that has a hydrogen on it. So Lone Ranger. So then when we graphed it, you guys see how when we wanted to graph carbon 1, we looked at what was adjacent? So when we wanted to graph carbon 1, we went to our adjacent carbon, which was a triplet, and we used the ppm that was given to us. You're not going to be asked to find your parts per million because, actually, I think you're given an equation, but your professors don't make you do it, right? I haven't heard. There's an equation, but like you guys don't do it. So yeah, you're given this, and you just graph it. So 5.77, you have a triplet, so we draw 3 peaks. On carbon 2, we looked at our adjacent carbon that had a hydrogen on it, and that we said was a doublet. So we went to 3.95, and we had a doublet. So we did 2 peaks. What makes something move downfield, and what makes something move upfield? Yeah, perfect, shielding. So what does that mean?
Like that oxygen is de-shielding that hydrogen.
Yeah.
Like in electron density.
Yeah, so now that I know that we actually have time, I thought that we were like so low on time. I can show you the little table that I made. And so we see that when we have low electron density, it leads to de-shielding, which is a downfield chemical shift. Whereas when we have high electron density, it's shielded and it moves upfield. So what does this mean? If you have high electron density, like you use the example of oxygen, that's very good. Well, it depends what you meant by oxygen, but yes. So I'm going to draw an example. If you have a carbon with hydrogen, 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 this is shielded pretty well because your nucleus is shielded. Your carbon is the most electronegative. This has the partial negative charge, whereas all of your hydrogen on the outside have partial positive charges, so it's shielded. If you had something like carbon, hydrogen, 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 but then you had a bromine over here, what's your most electronegative atom? Bromine, perfect. So you have bromine, it's like electronegative. That's causing your carbon to be kind of partially positive now because bromine is really, really electronegative. So this is going to be shielded or de-shielded? De-shielded?
Which one? De-shielded carbon.
Yeah, exactly. Yeah, exactly. So this is de-shielded because the bromine is pulling it away from the center. It's pulling those electrons away from the center. We have our dipole moment going that way. So this means we're going to be more upfield or downfield on an NMR graph spectrum. Downfield, perfect. If we compare that to what we just graphed over here, if I could find it again. When we graphed carbon 1, that was this 5.7 ppm, it was more downfield, right? Yeah, perfect. Because we have 2 chlorine here that's pulling the electrons away from that carbon center. So it's causing it to be de-shielded and thus it's downfield. Yeah? Whereas over here we only have 1 chlorine, so it's going to be more upfield than having 2 chlorine. So our carbon 2, which was this one at 3.95, is more upfield because it only has 1 chlorine pulling those electrons away from our carbon center. So it's still deshielded, but not as deshielded as carbon 1. Does that make sense? Okay. So, we still have 25 minutes. Do you guys want to do more NMRs, more spec? I could just go through like the rest of the sheet. So, yeah, definitely. Let's see. I showed you the NMR table, right? We did that. Do you want to do a spec question? Like a mass spec?
Yeah.
Okay. So, oh. So if we look over here, we already kind of went quickly through these, but we could go through it a little slower because those are important. Graph the molecular ion peak. M plus means molecular ion. M plus 1 and base peak of CH4. So when we're looking for our molecular ion peak, what we want to do is we want to find the weight of our given compound, which is CH4, because we said, if we go back to here, mass spec is identifying the molecular formula and weight of our compound. So we're going to find the weight. So CH4, we could just do this in whole numbers. So we all know that carbon is 12. We know that hydrogen is 1, so we have 4 hydrogen, and that's going to be 16, right? That's going to be our weight. So that's going to be our MZ ratio, which in this case is equal to our molecular ion peak. So your MZ ratio is like going to be your molecular ion peak. And how can we just make 16 our molecular ion peak? This is our mass to charge ratio, right? So Z is our charge, and that's going to typically be equal to +1. So we're really just looking for our mass. So over here, if we graph this, when we're doing mass spec, what's our x-axis? Oh, so that's no, you're good. That's our MZ ratio. Yeah, perfect. But yeah, the y-axis is relative abundance. Yeah, and our x-axis, MZ ratio. So if we're doing relative abundance, let's say we have 100, 80. I kind of wrote this in the way, so it's going to look weird, but 40, 20, 0, 0. Then let's say we have like 5, 10, 15, 20, 25. Our molecular ion peak is at an MZ of 16. So an MZ of 16 will be about here, because of course 15 is right there. And we don't know the relative abundance, so I'm just going to draw a line. And that's our molecular ion peak, and we know that because it's at 16. Our base peak, we can't really find it, but it's going to be the tallest peak. So it's going to be around 100. How do we find our M+1 peak? Yeah, exactly. So if our molecular ion peak is equal to 16, our M+1 peak is 16 plus 1, which is 17. So that's really all you have to do to find it. So we're going to draw another peak at 17. Now, are we going to make that a really tall line or really short? Really short, and why? That's okay. It's less abundant? Yeah, exactly. Because we're finding what kind of isotope? We're finding carbon-13, right? Which is much less abundant than carbon-12. So our M+1 peak is comparing M plus is carbon-12. M+1, we're finding carbon-13. That's why. So carbon-13 is much less abundant in nature than carbon-12. So it's going to be a very, very tiny short peak. M+1, molecular ion peak. And then this is our base peak, like we said. Yeah.
Is there any reason in particular you put your base peak there?
No, not at all. We can't find our base peak, so I just like wrote a random one. It just has to be the tallest peak in the structure. Yeah. Let's see. So we kind of did this one, but what was the reason that we had an M+2 peak? Yeah. So what we found, it was a 3-to-1 ratio. So what we found was chlorine. And we have chlorine 35. Our isotopes are chlorine 35 and chlorine 37. So 35 plus 2 is 37. So that's why we do M+2, because 35 plus 2 is 37.
And you knew it was chlorine because of mass?
Oh, so we knew it was chlorine because we have a base peak right here that's close to 100. So we know our base peak. Our molecular ion peak, its relative abundance is right here by 60. About by 60. Our M+2 peak is right here about by 20. So this is a 3-to-1 ratio, 60 to 20. See, 60 to 20, we could just write it as 3-to-1. So that's why we know it's chlorine. And like on an exam, it's probably not going to be labeled to you as base peak, molecular ion peak, and M+2 peak. You're just going to have to know, okay, I see that this has a ratio here of about 3-to-1. So you're going to have to just visually identify it. Like, they won't label it for you more than likely. So we have that. I think I had one of bromine, didn't I? Somewhere. It was like here. This was the one of bromine. As we saw, they were both at about a relative abundance of 60. So that's why we knew it was a 1-to-1 ratio. We don't go by MZ for the ratio, but we do see that it's like, I mean, I drew the lines kind of far away, like, but it's handwritten. So you just also want to make sure that it is 1 unit away from each other. Not that you have like one here and then one here. Those won't be a 1-to-1 rate. Those won't be bromine because they're too far away. You have to have them like really close to each other because you have to have their MZs the same. Was that English? Did I just confuse you guys? That made sense? Okay. Okay. So we did, let's see, we did spec, we did mass spec, we did NMR, we did CNMR. If we have something like 20, which molecule will have a higher frequency and in which direction will it shift? So we kind of did something like this. So CH4 is better shielded than CH3Cl because the chlorine is pulling the electrons away from the carbon center, because this would be drawn as, you know, hydrogen, 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 whereas this is hydrogen, 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 chlorine. So we have a dipole moment. That way it's pulling the electrons away, whereas here the electrons are on the inside. That's partial negative symbol, by the way. So which one will have the higher frequency? The so this one weighs less, right? So yeah, that's a good way to think of it actually. But the frequency, we could also think of it as frequency is inversely related to shielding. If this is something your professor goes over, I'm not sure, like it could be specific to your class. So yeah, frequency is inversely related to shielding. So if you have a high frequency, it means you have low shielding. So, oh, I'm sorry. That means this has a higher frequency. Your de-shielded molecule. Yeah, I'm sorry about that. Yeah. Did we do this one? Oh, okay. So we have to count how many carbons are in a new environment to find the number of lines on our CNMR spectrum. So this is like counting, if it says lines, it's like the number of signals. And again, with CNMR, no splitting. So it's when you have a CNMR graph, it's just going to be one line. You're not going to have doublets, triplets, etc. So what we're going to do here is we're going to count the number of carbon in a unique environment. So this carbon is in a different environment from this one, and these. So this is 1. So we have 1 here. This carbon is in a different environment from this one, and these. So this is another carbon in a unique environment. This one as well. It's unlike any other. And then these 3 over here, they're all in the same kind of environment to each other, but they're in different environments compared to this one, and this one. So how can I draw this?
So both of them are different?
So this gives 1 line. Yeah? So this is in a unique environment, unique. These are unique from these 3, but they're not unique from each other. So those just give 1 line. So we have, yeah, it's perfect. So answer equals 4 lines. Yeah. And like I said, if you see this on a graph, like if they ask you like identify which one's a CNMR graph, it's just going to be the ones that have 1 peak like that. Like you're not going to have doublets, triplets, etc. It's just going to be 1 line with CNMR. Can I switch? Yeah. Let's see if we have, I think we have time here for, yeah, we have like 10 minutes that we could do radical reactions. Oops, let me just look at something. Yeah. So we have ranked the following radical structures in order of most to least stable. So what are we going to do here? This is kind of reverse from, well, I don't want to say reverse, but this is kind of a new concept with radical reactions. So how do you rank the stability here? CBA. So you're absolutely correct that A is the least stable. But between C and B, which one is more stable? B? Why B? Well, so it has resonance capability. So it has resonance capability here because I don't think you get to this in Orgo 1, you do it more in Orgo 2, but what you can do, I'm just going to redraw this on the side for a second, just so you see how this has resonance. You have that dot there. You can kind of go and form bonds, and then this goes and forms a radical. So you can do resonance there. Whereas this one, it's not as stable. So this is more like conjugated. You can do more stuff with it because you have more double bonds here that can go and move around. Whereas with this, you only have like 1 option. It's not as stable. Did that make sense at all? So I'll just say this has like middle stability. Stability. So this is going to be B is greater than C is greater than A. Yeah. This is the last question on the worksheet. If we have We might have time to go back and do more synthesis, or like we'll just do like Q&A and whatever. Identify the following types of reactions as either hydrogen abstraction, addition to pi bond, or radical halogenation. Let me make this a little closer, maybe. Maybe that's better. So what's what? What's A? Well, nothing is labeled as A, is it? A, B, C. Did you say halogenation? Yeah, so that's that's radical halogenation. Because you put a halogen on it. Because if you like it, then you should have put a halogen on it. With B, what did we do with B? Yeah, exactly. Because we had a hydrogen hanging out over here, right? Chlorine took well, so we have the one-sided fish hook, whatever they call it, and then the other side went to that bond, and we got that dot, that one pair. It's not a pair, but the one electron that went there. So we took out a hydrogen, and one of the electrons went to this center, and the other electron went away with the hydrogen. Hydrogen abstraction. And like I always say, like in these cases, I'm half Italian, so the hydrogen, it just went away. So now we look at C. What is this? Is it hydrogen abstraction, addition to pi bond, or radical halogenation? Yeah, pi bond. What's a pi bond? Yeah, a pi bond's a double bond. So we added this radical to the pi bond. So this broke. That's my attempt at a half fish hook, I'm sorry. And then this went on this carbon here, and that makes addition to pi bond because we added a radical to where the pi bond would have been. Okay? Radical halogenation, we use heat or light. This is heat. This is light. And we formed a bond with that chlorine. Hydrogen abstraction, we took out a hydrogen, and we have a radical now, a tertiary radical. Now addition to a pi bond, we added a radical to that pi bond. That's the end of what I have here. We could go back and do synthesis. We have 7 minutes. So like, do you guys want to go back and do synthesis, or do you have any questions that you like specifically want to go over? Yes. Yeah. And like I have it here, just while you guys are setting up, on the table, you'll see evaluations. If you could evaluate Study Union and myself, if you could fill those out, and then you could just leave them on the table, and I'll collect them in the end. Do you have a question, Lean? What? Oh, thank you. Yeah. Number? Number.
42. It's under there.
Okay.
Oh, okay.
I've never done evaluation.
I don't know why that's there, but
Okay. Oh, thank you.
yeah, right? Make sure no robot is exactly what it's there.
That problem. So an unknown compound X has. Oh,